this lecture of the jet transformation. In this lecture I am going to discuss the inverse jet transform, and before that I will state two theorems. One is the initial value problem and another one is the final value problem. So initial value problem. Let jet transform of the sequence un is uz, then if jet transform of the sequence un is uz, then your u0 is equal to, then your u0 equal to limit jet tends to infinity of uz. Then your u0 is limit jet tends to infinity uz. Proof is very easy. We know that uz means the jet transform of un, and the jet transform of un is u0 plus un. We can write it as n equal to 0 to infinity un jet power minus n, and this is your u0 plus un upon z plus u2 upon z square plus u3 upon z cube and so on. So this is your uz. Now if we put limit z tends to infinity, then all these terms will be 0. So your u0 is limit z tends to infinity of uz. So this is your u0. And again from this equation we can have the value of un. Also our un will be, now if you take the u0 on the left hand side and then take z on the left hand side, then un will be limit z tends to infinity of z into uz minus u0. So this is your un. Similarly my u2 will be, if you multiply this z square here, then our u2 will be limit z tends to infinity of z square, then we will have uz. Take all these three terms on the left hand side. So the first term is uz, the second term will be u0, the third term will be minus z inverse un. And after that we have taken z square LCM. We have taken z square on the left hand side. So all the remaining terms will have 1 upon z. So as we will put z tends to infinity, all those terms will be 0. So your un means, take this u0 on the left hand side. So this left hand side will be uz minus u0. And if we take this z, if we multiply by z on the both sides, then we will get z into uz minus u0 equal to u1 plus 1 by z u2 and so on. And as we are going to put z tends to infinity, so all the remaining terms will be 0. That means we will get 1 upon infinity and hence it is 0. So these are the formula for u1 and u2. So this is known as the initial value problem. Then final value problem. So if the jet transform of un is uz, then your u infinity is equal to, or you can say that, okay, your u infinity equal to limit z tends to 1 z minus 1 of uz. U tends to infinity means when your n tends to infinity. Proof. Let us compute the z transformation of un plus 1 minus un. Let us compute the z transformation of this one. Now in the right hand side I am opening the definition of z transformation, and z transformation is n equal to 0 to infinity un plus 1 minus un into z power minus n. Now on the left hand side, in the left hand side, let us break this z transformation. So this will be a z transformation of un plus 1 minus z transformation of un. And here you can write it as n equal to 0 to infinity un plus 1 minus un of z power minus n. Now we have the formula for z un plus 1. Z un plus 1 was z The formula for Z1 plus 1 was ZU1 minus ZUZ minus U naught. This was the formula for ZU1 plus 1, which I have already given in the previous lecture. And Z transformation of U1 is UZ. Now in the right hand side, let us open this summation. Now if you put n equal to 0, then we will get U1 minus U naught, and Z power 0 is 1. Then if n is 1, then we will get U2 minus U1 Z power minus 1. If n is 2, we will get U3 minus U2. Okay. Before that, there is no need to open this summation because we have to put Z equal to 1. So this is this one. Now in the left hand side, let us take UZ common. So if you take UZ common, then we will get Z minus 1. Then this will be your minus Z U naught. And then we have n equal to 0 to infinity, U1 plus 1 minus U1 of Z minus n. Now let us take the limit Z tends to 1. So if you take the limit Z tends to 1, then we have UZ minus Z minus 1. Now if Z is 1, then this will be your U naught, and in the right hand side we will have n equal to 0 to infinity, U1 plus 1 minus UN. As Z is 1, so this will be your 1. Now limit Z tends to 1, UZ Z minus 1 into UZ minus U naught is equal to, if you put n equal to 0 here, then this will be your U1 minus U naught. Then we will have this is your U1 minus U naught. Then we will have n equal to, for n equal to 1, this will be U2 minus U1. Then for n equal to 2, this will be your U2 minus U3 minus U2. And then we will have another term, UN plus 1 minus U1, then shown. Now let us take n tends to infinity, then we can terminate this series up to this nth term. Now here you can see that, okay, let us write this series again. So this will be your U1 plus 1 minus U1. Now our n will go from 1, 0 to infinity. So all the remaining terms are there as n tends to infinity. So there is no need to write the remaining terms as we have n tends to infinity. Now here you can see that our U1 is cancelled, U2 is cancelled. So all the terms will get cancelled. We will have just this U0 and this UN plus 1. So on the right hand side we will have n plus 1, n tends to infinity. We will have minus U0, and here we will have UN plus 1. This U0 is constant, so we can write it as U0 plus limit n tends to infinity of UN plus 1. Therefore, now this U0 and this U0 will get cancelled. Therefore, if you put n tends to infinity here, we will get infinity plus 1, that means infinity equal to limit z tends to 1, z minus 1 of uz. So this is your final value problem, and we can also write it as, limit n tends to infinity of un is equal to limit z tends to 1, z minus 1 of uz. So this is the z transformation of this is the final value theorem for the z transformation. Now inverse transformation. Inverse Z transform. So because as we know that Z transform of un is equal to uz, so basically the Z transformation of uz will be the sequence un. So we have to evaluate the sequence un. Now first method is Z transformation using inverse Z transformation using partial fraction. Inverse Z transform using partial fraction. So question, evaluate Z inverse of evaluate the inverse Z transformation of 2Z square plus 3Z divided by Z plus 2 and Z minus 4. Let us evaluate the inverse transformation of this function. Solution. Let us assume this bracket as uz because we have to evaluate the inverse Z transformation of uz. Let uz equal to 2Z square plus 3Z into Z plus 2, Z minus 4. Now here you can see that the degree of the numerator and denominator is same. So either you can divide this numerator by this term and then take the inverse transformation, or let us take this uz upon z. Now if you take uz upon z, then in the right hand side we will have 2z plus 3 divided by z plus 2. And let us find out the inverse transformation of this. Let us break this using the partial fraction. So this will be your a upon z plus 2 plus b upon z minus 4. So this is equation number 1. So we have, so from here we have a into z minus 4 plus b into z plus 2 equal to 2z plus 3. So if we put, if z equal to 4, then you can say that b equal to, if z is 4, then this will be your 11 upon 6. If z equal to 2, then if z equal to minus 2, then your a, if z is minus 2, so then this will be your minus 6. So now this is your minus 2, so this will be your 1 by 6. So our a is 1 by 6 and b is 11 by 6. So therefore uz upon z will be a is 1 by 6, z plus 2, then b is 11 by 6 and 1 upon z minus 4. So this is equal to, now let us cross multiply this z. So this will be equal to z upon z plus 2 11 upon 6 into z upon z minus 4. Now we have the inverse transformation for, we know that, note, we know that the z transformation of a for n was z upon z minus a when your n in is greater than or equal to 0. So the z transformation of 8 for n is equal to z upon z minus a, and it is true when your n is greater than or equal to 0. So from here your z inverse of z upon z minus a will be 8 for n and your n should be greater than or equal to 0. Now, so taking inverse, so this will be your 1 by 6 z inverse of z upon, now this term can be written as like this, and here we will have 11 upon 6 and then z inverse of z upon z minus 4. So this is equal to 1 by 6. Now this z upon z minus a inverse is 8 for n. Now a is minus 2, so this is your minus 2 for n plus 11 by 6. Here our a is 4, so this will be your 4 power n, and this is your answer where my n is greater than or equal to 0. So this is the solution of this problem. Then let us find out the inverse z transformation using the convolution. And convolution method is quite easy because in partial fraction there are some confusion. So I am using the convolution theorem for the inverse z transformation. That means I am using the residual theorem for the inverse z transformation. So inverse z transformation using integral formula. I am using this integral formula because it is quite easy to operate. So we will try to solve the maximum questions with the help of this method. The inverse transformation of uz, that means this sequence un is equal to 1 upon 2 pi I integral uz into z power n minus 1 dz. So this is equal to integral 1 upon 2 pi integral uz z power n minus 1 dz. Now this means the value of this integral will be 2 pi times the sum of the residue. So as we know that the value of this integral, now we know that with the help of the residue theorem, the value of this integral is 2 pi I times the sum of the residues. So 2 pi I will get cancelled. So it is equal to sum of residues of this function uz into z power minus, I think this will be minus n, not okay, of z power n minus 1. So sum of residues of this function, for at poles of uz which lie inside the contour C, for according to your region of convergence. So the integral 1.2 pi I integral uz z power n minus 1 dz equal to sum of residues of this uz into z power n minus 1 at the poles of uz. Now if the pole is simple, then we will have a formula. If the pole is of order n, then we will use a different formula for residue. You know that the residue, I am giving this formula for the residue. We know that the residue of the function fz at z equal to a at simple pole, that means when your pole is of order 1, at simple pole z equal to a is equal to z minus a into fz, and the value of this integral at z equal to a. So residue of fz at simple pole z equal to a is this one. This is your formula. And then residue of fz at pole of nth order at z equal to a is residue of fz at pole of nth order at z equal to a is equal to 1 upon n minus 1 factorial dn minus 1 upon dz power n minus 1, then z minus a power n into fz, and the residue at z equal to a. So if the pole is of nth order, then your residue will be 1 upon n minus 1 factorial d power n minus 1 upon dz power n minus 1 means the nth minus, so that means the n minus 1th derivative of z minus a power n into fz. So this is for when your residue is of order n, when your pole is of order n. Let us compute the inverse z transformation of question. Evaluate the, let us write question here. Evaluate the inverse z transformation of, the first question is 4z square minus 2z divided by z cube minus 5z square plus 8z minus 4. And then the second question is evaluate the inverse z transformation of z square plus z of divided by z minus 1 z square plus 1. So let us compute the inverse z transformation of these two problems. Solution. So the inverse Z transformation for the first part. Before that, let us find out its factor. So the Z transformation of 4z square minus 2z upon z cube minus 5z square plus 8z minus 4 is equal to, now here you can see that if we put z equal to 1, then this will be 1, this is your minus 5, so this will be your minus 4, and this is again your minus 4, so that will be your 8, and it is your 8. So z equal to, if you put z equal to 1 here, then that means z minus 1 is a factor of this one, so we can write it as 4z square minus 2z upon z cube minus z square minus 4z square plus 4z minus 4. So that means this is your z inverse of 4z square minus 2z upon, now from here we will have z minus 1 so this is your 4z square minus 2z divided by z minus 1. Then in the bracket we will have z square minus 4z plus 4, which is your z minus 2 whole square. So this is your problem. Now here you can see that your z equal to 1 is a simple pole and z equal to 2 is a pole of order 2. So now the inverse Z transformation, so this will be your un. Now this un is equal to sum of residues of, say this is your uz into z power n minus 1 at z equal to 1 and z equal to 2. So the answer of this problem will be, so sum of the residues of uz into, say this is your uz, which is your function, original function. So uz into z power n minus 1 at z equal to 1 and z equal to 2. Here your z equal to 1 is a simple pole and z equal to 2 is a pole of order 2. So now this is equal to, let us find out the residue at z equal to 1. At z equal to 1, your residue of uz into z power n minus 1 at z equal to 1 will be, multiply the function by z minus 1. So if you multiply the function by z minus 1, then this will be basically z minus 1 of uz into z power n minus 1 and the value at z equal to 1. So this is equal to, now put the value of uz. So this z minus 1 will get cancelled and we will have z power n minus 1 of 4z square minus 2z divided by z minus 2 whole square, and this value at z equal to 1. So if you put z equal to 1 here, before that let us take this term in the bracket, so this will be 4 z to power n plus 1, then here we will have 2 z to power n divided by z minus 2 whole square. So if you put z equal to 1, so this will be your 4 minus 2, that means 2, and at z equal to 1 this will be 1 minus 2 whole square, that means 1. So at z equal to 1, our residue is 4 into 1 power something is 1 minus 2, so that means 2 divided by 1. So the residue at z equal to 1 is 1. Now please note that here let us choose the contour large enough so that these two poles lie inside your contour. Please note that here we are assuming that these two poles lies inside the contour C. So we are choosing the contour structure large enough so that it contains both the poles. So we have taken a large enough contour and assuming that these two poles are inside C. So at z equal to 2, now here z equal to 2 is a pole of order 2. So if this is a pole of order 2, then use the formula. Now residue of fz, residue of uz into z power n minus 1 at z equal to 2. As this is a pole of order 2, so we will use formula n minus 1 factorial. So this means 2 minus 1 factorial into d by dz of z minus 1 whole square into uz of z minus n, and the value at z equal to 2. So this is equal to 1 d by dz of, now your uz was, my uz was 4z square minus 2z upon z minus 1 whole square z minus, so this was z minus 2 because we are finding at z equal to 2. So your uz was 4z square minus 2z divided by z minus 1 into z minus 2 whole square. So z minus 2 whole square will get cancelled. So this is your z minus 1, and here we have z power n minus 1. Now if you multiply this z power n minus 1 here and the value at z equal to 2, so we will have 4 z power n plus 1 minus 2 z power n divided by z minus 1. Now by differentiating, we will have 4n plus 1 z power n, then this will be 2n z power n minus 1, this is your numerator, into z minus 1, then 4 z power n plus 1 minus 2 z power n divided by z minus 1 whole square, and we have to calculate the value at z equal to 2. So let us put z equal to 2. So at z equal to 2, we will have 4n plus 4 into 2 power n. Here we will have 2n into 2 power n minus 1. Z is 2, so this will be 1 minus 4 into 2 power n plus 1 minus 2 minus minus plus into 2 power n. And here we will have 2 minus 1, so that will be a 1. So this is equal to, so this is equal to 4n 2 power n, 4n into 2 power n plus 4 2 power n. Here we will have, now this 2 can be taken in this power, so this will be minus n into 2 power n. Here we will have minus 2 times 2 power n, and this is your 2 into 2 power n. So this is your cancel, and this will be your 3 times 2 power n plus 4 2 power n. So that means this is your 3n plus 4 2 power n. So therefore your answer is, hence our answer is, I think there will be 3 answers, 3n minus 2. This, so that means there will be minus 4. There will be minus 2. Now this is your 4n, and this is your 4 2 power n minus n 2 power n, and here this will be your 8, not 2. So this is your 2 power n into 2, so this will be your 8. So this is your 8, not, now this will not get cancelled. So this, that means 4 plus 2 is 6 minus 8, that is your minus 2. So here we will have minus 2 into 2 power n. So this will be your minus 2. So your answer is, therefore the un means the z transformation of 4 upon z minus 1 into z minus 2 whole square is equal to the sum of the residues. The first residue was 2 and the second residue is 3n minus 2 z power n, where your n is greater than or equal to 0. So this will be your answer.